All right, my friends, let's take another look at example 1. Starting with a different way to draw it, if going in, you know that you're going to use the cylindrical shells method. And we'll talk later about how kind of to know going in which method you're using. It kind of has to do with this little light of mind thing that I showed you a little bit ago, but we'll talk about it a little more soon. Okay, you still draw the 3D shape pretty much the same way that you would have before. Okay, so you draw this pretty much the same way as you would have before, except the part where you draw that washer, okay? So here's the deal. If you're doing for this problem, if you're doing a dx integral, the trick is to show that dx rectangle that you'd be working from. So draw, kind of an infinitely thin, use your imagination, infinitely thin rectangle somewhere in the original shaded region that you started out with, okay? And then you're going to show what happens when you rotate that infinitely thin rectangle all the way around the y-axis or whatever axis of revolution you're given. And then you just show kind of the shape that would be created. There you go. And then you can see that little cylindrical shell. So if we can find a formula for the lateral surface area of this cylindrical shell, then all we have to do is add up infinitely many, infinitely thin of those, imagine them stacked one on top of the other as they kind of grow in height according to the function, and then we'd have exactly that bundt cake created, okay? We would have found exactly the volume of that bundt cake. Okay, so let's get started. Here's the plan. We are going to add up infinitely many, infinitely thin cylindrical shells. What's the formula for the lateral surface area of a cylindrical shell? It is 2 pi, which I'm going to factor out front since it's a constant, times the radius, times the height, and then we just have to integrate with respect to the appropriate variable. I'll just say with respect to whatever is appropriate, and then use appropriate bounds as well. And that's going to be the volume according to the cylindrical shell method in words. Now, you could always memorize multiple formulas, but I've found that the words are easier, and then the formulas kind of fall into place if you know what you're looking for, okay? So let's fill in, for example, the radius here. So look at your picture, what does it look like the radius is of that cylindrical shell? Well, I claim that it's just the x coordinate that it would take to get onto the original region. It's exactly the x coordinate. And so I would put x in this case in place for radius. What's the height? Well, looks to me like it's the distance from the x-axis all the way up to a point on the parabola. And so that would just be the y-coordinate, but we're doing a dx integral, so we're going to put that function of x in there for the height. And then we have decided the appropriate variable of integration in this case would be dx. And now that we've declared it a dx integral, what bounds would make sense? Well, we're going to start by, adding in the area of the integrals that you get from 0, and then we'll go all the way out at kind of adding these. You just keep stacking them, And so we want to go all the way from the rectangle that we get when x is 0. Where do we want to stop? Yep, when x is 6. There we go. Okay, and this would be your setup, and then it's just a matter of punching that into your calculator. So go ahead and do that. Don't forget on this one to multiply your integral value by 2 and by pi. Let's go ahead and take a second and do that. You want to practice it as much as possible so that it's muscle memory, so that you are way less awkward with your calculator than I am. That's the goal, my friends. Hopefully some of you are already there. Okay, so I did the integral. I got 108. I'm going to multiply it by the 2 that's in front there. I get 216 pi. It's volume, so let's say units cubed. And then let's have that habit of multiplying pi n as well. And so you'd get approximately 678.584 cubic units. There we go. All right, my friends, I hope that makes sense. As we move forward, let's make sure you're okay with the formula that we're going to use. Let's go ahead and state it clearly here. The formula for volume using the cylindrical shells method is volume equals 2 pi times the integral from appropriate bound to appropriate bound of, and we're just going to learn this in words, radius of the cylindrical shell times the height of the cylindrical shell, and then with respect to the appropriate variable. And we'll talk about how to figure that out in a little bit, okay? And when we're at it, let's actually make it official. What's the formula for the volume using the washer method? And we could have a different formula for a disk method, but I don't know why you would. Anyway, so what was that? That was pi, notice instead of 2 pi, times the integral from appropriate bound to appropriate bound of, and we're going to do this in words to avoid needing to memorize a bunch of different formulas. So, oops, let's remember the right words though, shall we? Outer radius squared minus inner radius squared with respect to appropriate variable. There we go. These are the next 2 formulas for your flashcard collection. I recommend you memorize them now before we proceed to the next example. If you need to, pause the video to make sure you've got these nice and memorized. And assuming you've got them memorized, let's take a look at example 2 here. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. Part A, using the shell method, and then part B, using the disk or washer method. All right, see how it goes. Check in with me in the next video.